the next portion of our conversation about gases will go on then to further parts of our learning objectives. We'll need to look at ideal gas law and where it comes from, and how you relate final pressure volume moles or moles of gas to an initial pressure volume moles or such in temperature of a gas. We will also eventually get ready to use the ideal gas law, but that will come a little bit separately. When we're describing things about gases, trying to understand what they're doing, we'll talk about gases being ideal, and that's kind of a hypothetical thing, but most gases are going to be somewhat ideal, reasonably close to that assumption. A gas whose behavior follows gas laws exactly. We'll describe some gas laws as we go. And the properties of the gas that we'll be studying or describing to understand what's happening with a particular example are pressure, temperature, volume, and numbers of moles, shown with P, T, V, and N as the variables that will be measured in each of these conversations. The first of the gas laws, and don't worry about remembering their names, is called Boyle's Law, and is represented by the picture with the pistons and the cylinders on the right. If you have a situation where there's initially one pressure of atmosphere is one pressure, so one atmosphere is the pressure, and the volume is 1 liter. You change the pressure to 2 atmospheres, now the volume is smaller, it's half a liter. Well, this is telling us the relationship between pressure and volume that we described as Boyle's Law, where at constant number of moles and temperature, the volume of the gas decreases proportionally as the pressure increases, and so as the pressure doubles, the volume is halved. And that's the way we like to think about this relationship between pressure and volume. And the name for that is Boyle's Law, but you don't have to fuss over it. You can say pressure is inversely proportional to 1 over volume, or volume is inversely proportional to 1 over to the reciprocal of pressure, as long as number of moles and temperature are constant. And another way of using that is to say pressure 1 times volume 1 equals pressure 2 times volume 2, which fits with the examples shown at the right. So at constant temperature and constant amount of gas, that kind of property will hold. Another way of looking at that relationship is to plot it. So if you plot pressure versus volume versus pressure, whichever way you say it, as shown on the left here, you get a hyperbola. It's certainly not linear. But if you plot at the right volume versus the reciprocal of pressure, then we have a straight line, which is why you can say why you can say that volume is related to 1 or proportional to 1 over pressure. That's why you get a straight line. So we're going to use this kind of thing where we talk about the initial pressure and volume being equal to the multiplied together, the product of the final pressure and volume. All right, let's look at an example that has pressure volume measurements on a particular gas sample at a constant temperature and number of moles and temperature. That's what N and T are. So if you look at the first one, we have 760 and 1, and then we have 380, which is half as much, and 2, and then we go down even more, and 3. Well, guess what? There's a pattern going on here. And so as the pressure goes down, the volume goes up. Does that look like, see what you mean? And if you did it mathematically, you could determine that pressure times volume is in fact a constant. K is just a constant. Or we can say pressure 1 times volume 1 equals pressure 2 times volume 2. So that's one of our relationships that we like to be able to use in calculating things for situations with different gases. What if we took instead and looked at the relationship between temperature and volume? This is a different set of values. We have a gas sample now with constant number of moles and pressure, but if we look at the temperature on the left and the volume to the right, what happens as the temperature goes up? The volume also goes up. Notice that temperature has the units of Kelvin. That will be important for gas laws or gas discussions, and the pressure keeps going up, the volume keeps going up. Due relationship. So that's another gas law. It's called Charles's Law, but don't panic about the names again. And so what it tells us is the following. represented by the pistons in the picture, at constant number of moles and pressure, the volume of the gas, of an ideal gas, changes proportionally to its absolute temperature. That means Kelvin. And so if the temperature doubles, the volume doubles. If the temperature is half, the volume is half. So what are we looking at here? We have a temperature of 200 to begin with, a temperature of 400 at the end, and so you go from a volume of 1/2 liter to a volume of 1 liter. So as the temperature doubles, the volume also doubles. So volume is directly proportional to the temperature. Another way of looking at that is to see the graphical relationship between volume and temperature. You get a linear relationship, a direct relationship, as long as the number of moles and pressure are constant. That's key, or this relationship won't hold. And so, whoops, sorry about that. I wanted to make sure I finished this diagram. And so another way of using this is to say that the relationship between volume and temperature, the ratio of volume and temperature at a first set of conditions will be equal to the ratio of the volume to the temperature at a second set of conditions. You can do this in Celsius, or you can do this in Kelvin. You'll still get a linear plot because the size of the degree is the same. But we're going to use Kelvin as much as we for most of our gas law calculations. All right, so let's take an example and see how we can use this. So if we have a mole of gas and we're given a temperature of 25 Celsius and 0.9 atmospheres, that's our pressure. There's our temperature, and there's the number of moles. We're challenged to look at this as spheres representing the gas in the piston in the diagram. And it's in an apparatus that has the movable piston, otherwise this would be an irrelevant question. Which set of conditions will result in a lower piston position than is shown in the drawing? Okay, let's look at our different choices. If you have 1 mole of gas, that's what we had to begin with, and 25 degrees Celsius, but now the pressure has gone up. That would be twice the pressure, right? So 2 times the pressure 1, isn't it? That's pressure 1 is up here. So if the pressure is doubled, what you expect for the volume? Well, that means the volume should go down, and that is in fact the answer for this question. But let's see what the other ones will do. Let's think our way through it. So if we start with 1 mole of gas, which is what we have over here, and we now go up to 50 Celsius, that's twice the first temperature, isn't it? And so if the temperature goes up, the volume should go up. So volume will be increased, and the pressure is left the same here, but the volume increases when the temperature increases. It's not that choice. If you double the number of moles of gas, so the number of moles now is 2 times the original number of moles, and so that means that the volume will also increase. When the volume increases, the number of moles increases, the volume increases. And the last example, if you keep, that one looks the same. Oh, no, it doesn't. If you have twice the number of moles of gas, but you increase the pressure, that does what? No, it doesn't. It's the same. Oh, I didn't read the previous example correctly. This is half the original pressure. So 1/2 of the original pressure. What does that do? Well, half of the pressure means the volume will also increase. So 2 reasons the volume will increase on that one. The volume will increase by decreasing, 1/2 the pressure. I didn't read the last column carefully. And then the fourth one, if you have twice the number of moles of gas, the same temperature, and the same pressure, the volume does also increase. Okay, you can calculate those out, but we get the general qualitative idea, and that's not so bad. That's a good place to go. Okay, so we didn't finish this in the right order, sorry. The Avogadro's law is the one that tells you about volume and the number of moles. Avogadro's has to do with moles, right? And so at constant temperature and pressure, what's the case? Then the volume of the ideal gas is going to change proportionally with the number of moles. So if the molar amount doubles, the volume doubles. And if the molar amount is halved, then the volume is halved. So that helps to explain the previous example. I had my slides in the wrong order, sorry about that. So if you have the same pressure for two situations, pressure and temperature have to be the same, right? And it's not specified here what the temperature is. But if you go from 1 mole to 2 moles, the volume then becomes twice the original volume in the cylinder for this example. So you have to add actual gas to the experiment to do that. So the relationship between volume and the number of moles is a constant. Or we can relate this again to initial and final conditions. The ratio of volume to moles to begin with related to is going to be equal to the ratio of volume to moles at a second set of conditions. We call that Avogadro's law, but we're not memorizing names of laws. That's not the point here. So in summary, we have 3 laws. Some people call them the ABCs of gas laws. The last one was A. Avogadro's law relates volume and moles, and the Boyle's law was the first one we looked at, where it's relating pressure and volume to one another, and you can take 2 sets of conditions and come up with a calculation for each of them. And the third one is Charles' law, where you can relate volume and temperature. Nobody needs to memorize the names. That's quite beyond our concerns. So these gas laws are going to be used in combination with one another in our next section to describe the ideal gas law. I hope these are helpful to you. Please ask more questions. Keep me posted if there's things that don't make sense. Ask more questions, and I'll see you in class.